will give some small definition about clocks, and then I will go through the transmission lines, and at the end about clock termination techniques. And the transmission lines I will only do a very, very, very basics, because the transmission line theory is a very huge theory. And last time I recommended you a book that's called Microwave Engineering. There you can read a lot about transmission lines and the theory behind the transmission line. So let's start with the clock. You know already that an ideal clock looks like this. And the important thing is that this ideal clock has infinite bandwidth. And for PCB, infinite bandwidth is not so good. Therefore, we have like this one. So it's a real clock. And the real clock have a defined bandwidth. And at the end, it's very important to know how defined it is. And we have also a rise time here and a fall time. And the rise time is defined from 10% to 90%. And also the fall time. In some books, they also define it from 20 to 80%. So if you are reading the theory, it's very important to see first how they define the rise and fall time. So now one thing is the duty cycle. The duty cycle is the percent area of this one compared to this one. For example, here we have 50% high, 50% low, and this is one clock period. So from one high and one low. And if we have 30% duty cycle, then we have here 20%, here 70%. I think this is more important for PWM signals. So for our clock signals, it's not so important. The more important thing is the jitter. So if we have here an idle event, then the jitter is defined as the non-idle event. That means that sometimes it rises faster or a little bit slower. And the maximum and minimum point here is called jitter. So the jitters, we have always the jitter. And the jitter is also very important for matching. Or different. If you do a mismatch, then you have a higher jitter. So and if you want to measure a clock signal, for example, with oscilloscope or spectrum analyzer, then you often see like this. This is called I diagram. With the I diagram, you can read everything, the most thing. So you can see the distortion here. This is a distortion of the highest point. And you can see the fall time and the rise time and the fall time, as well as the signal to noise ratio from distortion to the middle signal. And this point here, this is called a jitter. So normally you want to increase the I here. So you want that the I is as large as possible. And inside the I, this is the best operating point at this here for sampling and so on. Because here at this point you have the best signal to noise ratio. You can see from this point to this point you have the biggest range. Therefore, this point here is the best sample point. So, and if you want more information about digital signals, you can go to this site here. There's a PDF about digital signals. So each definition and a little bit about I diagrams and so on. So maybe this is very interesting for you. And so we have for clock some important formulas. One formula is the bandwidth of the clock. And the bandwidth is easy 0.35 divided by the rise time. And with this formula, you get the bandwidth of your clock signal. Another rule estimation is to take the 9th harmonic of a signal. And for example, if you have a 20 megahertz clock signal, the 9th harmonic is 180 megahertz. And maybe you already know it. If you have a clock signal and you do a fast Fourier transformation, then you have here one point. Let's say this is 1 gigahertz.
Put the PDF board one into.
there was something in the chat. So will you please explain a little bit more? I can try to say more. But first I will finish this one. So if you have on a clock 1 gigahertz, then of course you have some harmonics here. If this axis is logarithmic. So, and if you cut, for example, here with a filter, then you have not a rectangle clock, then you have a more like this. And if you go, for example, here, then it looks more like a clock, but with an overshot and undershot here. Therefore, you want to take the maximum harmonic. And if you take the maximum harmonic, of course, then you have a higher frequency, and it means that at the end you need a transmission line to get a real clock. So one question was about the jitter. The jitter is only the, you can also say, the noise of the phase. That means that the phase here is very noisy, so you have not exactly 50% duty cycle, you have a duty cycle about 49% to 51%. So at every step it changes a little bit. So therefore you can say it's the noise of the phase or the noise of the duty cycle. So you have a variation here at this point. If you have 50%, then the next time you have 94%, then you can say 25%, and then here 95.5%, and so on. So this clock is not ideal at each point. And the minimum maximum thing is then called jitter. So, and why we need this formula? It's very important to decide whether we need the transmission line or not. It means if the lambda, so the wavelength divided by 10, is bigger than the length of the trace, then you need a transmission line. You can see if you take some more harmonic, then you have a higher frequency. That means if your trace is long, then you need transmission line. And for transmission lines, you have to take care about matching. But we'll talk a little bit later about it. So another thing, very important thing is current. Let's say we have here clock generation. Here have your load, a capacitor, and we know that the capacitor is 100 picofarad, and we want a rise time about 100 picoseconds, and we have a maximum voltage at this point 5 volt. So how large is the current here? It's very easy. You know that the current is defined as the capacitance times the change of the voltage divided by the change of the time. Means at this time here, this is our rise time, the step here is 5 volt, from 0 to 5. So that means here dt is then the rise time and dv is then the step time, so it's the step voltage from 0 volt to 5 volt. So here our 5 volt. And from this given values, we need then 5 ampere. So that's a lot. So, but normally microcontrollers gives only 50 milliampere. This is very often used. So for 50 milliampere, you can only have 10 nanoseconds rise time. That means you have a limited bandwidth. If you have a 100 picofarad cap, of course, if you decrease your cap here, you can have a higher rise time, or also it means a higher clock frequency. And normally you will always have minimum or approximately 10 picofarad because of ESD structure, the fat gate biocapacitance, or all the fat capacitance of your second system. So let's talk a little bit about transmission line. So we will discuss here only two types of transmission lines. One is the microstrip, one is the differential microstrip. These two types will often used in PCB designs. Of course, it exists more types. For example, if you have a more layer PCB, then you have a microstrip inside the layer. Or if you have ground in right and left side. But then you have to know a lot about the waveguide theory and so on. Then you have to read the microwave engineering book. And the transmission lines are often used for impedance matching. That means you want to deliver the maximum power. If you have a mismatch, it means that at your sink, you have not 100% power, you have maybe 80% power, and 20% power goes back to your source. And this can also destroy your source. It's very important to know. So here's an important formula for the reflection. That you can see here, this is our transmission line. And here we have our load. So if our transmission line impedance Z0 is equal to Z load, then we have here 0 divided by 2 ZL. That means this is 0. So we have no reflection. We have a perfect match. And if you have, for example, a mismatch here, let's say ZL is 2 times 0, 0. Then you have ZL divided by 3 ZL. So you have approximately 1/3. That means 2/3 of the signal goes here and 1/3 goes back. So your sink here don't see the whole energy. You think one part of the energy. And if you have a very sensitive source here, then the 1/3 signal can destroy your source. Because normally your source cannot receive energy, or is not built to receive energy. So this is one example of a microstrip. If we have here our PCB, let's FR4. Here we have a background, and here's our line or a trace. Then the impedance can calculate it with this formula. So the important thing is to know is that if you have short lines, it means you don't need transmission lines. The energy is delivered by the trace here, so it flows here. But if you have long traces, then you generate here magnetic field and electric field. So the energy transport is then not in the trace, so in the cover. The energy transport is inside the FR4. And therefore, we need the theory, the impedance matching. I think you learned it also, or it's called like pointing vector. And this is the same thing for differential microstrip. For differential microstrip, you have two formulas. One is the same like the microstrip. This is here. This is impedance from this trace referred to ground. And the second one is a differential. So from this trace referred to this trace. And you see also that we have here Z0 inside. And of course, the distance between these two traces. So Of course, you don't need to do hand calculation. There's a free software, it's called Saturn PCB. With Saturn PCB, you can calculate your impedance. So you can put your distance, your height, your width, your thickness, and you can say, okay, I have also load impedance, and then it calculates your reflection factor, or it calculates how long your line can be, or what is the width of your line, or what is the d of your line, or the distance between these two lines. So it's a very nice tool, and with this tool you can also calculate other things like thermal thing, or how much current I can use for my line, and so on. And if you need more information or more theory, you can also go to this site, so Everything RF. There's also a lot about digital signals and so on.
यत्रो थ्योरी पढाउनु लास्टमा गएर सिधै क्याल्कुलेटरको दिइरहनु सफ्टवेयर दिइरहनु भएको छ कि
For some communication like UART, SPI, I2C, and so on, you don't need transmission lines because the signals are normally very small. So the clock frequency is very small if you let these lines very short. And for other digital communication like USB, for USB you need a differential microstrip, and you have to take attention about the mismatch because the differential impedance should be 90 ohm. Or for HDMI, Ethernet, PCI Express, and so on. For this one, you need transmission lines because we have here normally very high clock frequency. And if you have long lines, then you have to think about line driver because long lines has also resistance, so you have also voltage drop over the line. And with line driver, you push it again high to the upper array or to the lower array. And because of the traces and the parasitics, you have also lost energy of your clock. And with line drive, you can put again energy in your line. And here's one measurement example how a mismatch looks like. So this blue one is if you have a very hard mismatch. So you see you have an overshot and an undershot. So if your normal signal is here, then this one is a overshot and this one is an undershot. And if you do a better mismatch, then it looks like here. So you have a small overshot, and if you're perfect matched, then your signal looks like here. So perfect matching. And the mismatches, you can see why it's very important. If you have overshot or an undershot, you can go lower to the threshold and you can lose some bits. And of course here also. So there exists also two important clock termination techniques to help matching. And the important thing for matching is, of course, you have normally a synchronous system, and you want to maintain the synchronous system. And if you have a poor matching, then of course, as I said, overshot and undershot can occur, and also ring back the beats. Energy goes back to your source. And for some clock termination theory, you can go to this site, or this is a white paper, and there are some clock termination techniques and some theory behind it. But I will also show you two techniques. This is also the last stuff today. So one technique is a series termination. That means you have here transmission line, your source, sink, and directly after the source, you put the resistance. And the disadvantage of the system, this resistance, is that you will decrease, or you will lose the falling and rising time. And of course, the jitter can increase because you have here a small voltage drop. And normally this resistance is about 20 to 40 ohm. And you can also use it for very slow signals like SPI, I2, and so on. And I can recommend you, if you have designed a system, always put resistance after your source. You don't need to put 1, 2, or 10 ohms. You can also put 0 ohm. But if you design then your PCB and then measure the clocks and you see, okay, I have a mismatch, then you can put here some small resistance to match your system. So it can help you for your prototyping a lot. And here's one example. Here's one example if you have a 22 ohm resistance. So you see you have a small overshot and undershot, and you have a settling time here. And if you increase the resistance here, you can decrease your overshot and undershot. And also the settling time is a little bit faster. So this small resistance can help your matching. And roof, you can say, okay, the resistance should be Z0. This is my line, minus the source impedance. So this is more matching between these two things. Other technique often used is an AC termination with a resistance and a capacitance. You can also say, okay, you don't want the capacitance, you have only resistance, but the problem is then that you have here a current flow and a voltage drop. So a DC voltage drop. And you don't want lost power on your line. Therefore, you put a capacitor inside here. I think there was like a question. No. So here you have to say, okay, your resistance.
यसको बारेमा यो जुन इम्पिडेन्स म्याचिङको जुन सफ्टवेयर छ त्यो के फ्री हो?
Your resistance should be equal to your transmission line impedance for a good matching. It means if you have 5 ohms here, then you also need your 5 ohm. This is very nice if you have a sink whose impedance is very high, like 5 mega ohm. And if you have 1 mega ohm and 50 ohm parallel, then it's roughly 50 ohm. So you have a very good matching. And this cap here should be small, that no current flows into the cap, and also not too large, because large caps means that you have a higher bandwidth, or of course a higher delay. Not a higher bandwidth, you have a lower bandwidth. And you can see the effect of source resistance if the source resistance is too small or too large. Here on the top picture, you see what if my driver is too small, so the resistance compared to the line impedance. That means you have a very long delay, so it takes long time to go to the upper rail. And if your driver is too large, then you have, of course, over and undershot, and also a very long ringing here. Sorry, not long settling time. So if you design your PCB and measure it, and you see this one, then you know, okay, my driver is too large, so I have to increase my series impedance or my AC termination. Question in the chat? Question is the impedance matching software free? Yes, the software is free. So this is a website you can download here for Windows, and I think this is only for Windows.
Matching software, certain PCB design toolkit.
Yeah, and this looks like this here. So you have a lot of things to change. You can also calculate your wire, your time management, and also the wavelength calculator. And they have a new thing about crosstalk, but I don't know whether this is very good. And of course, you can see here line calculations. So I can highly recommend you to download this tool and to check the tool and design with this tool, because it's a very interesting tool.